In the previous section, we were able to find circulation and flux using line integrals and a parameterization of the curve. We were able to manage it, but it was quite a bit of work. So we're hoping we can find an easier way. And the answer is yes, there is an easier way, because there's two new forms of the fundamental theorem of calculus that we first learned in Calculus 1 that we need to learn now. There are two forms for line integrals, a circulation form and a flux form. However, you're not going to be able to use these all the time. You can only use them in specific circumstances, namely that your vector field is something called conservative if you're looking for circulation, or source-free if you're looking for flux. All right, so let's begin with what a conservative vector field is. A conservative vector field has a potential function phi such that the vector field is equal to the gradient of phi. So in 2 dimensions, what does that mean? It means that if your vector field is f comma g, then the derivative of f with respect to y is equal to the derivative of g with respect to x. In 3 dimensions, it's more complicated. So you need f sub y equal to g sub x, f sub z equal to h sub x, and then g sub z equal to h sub y. All right. So let's test whether these particular vector fields are conservative. And if so, then we're going to find the potential function phi. All right, so let's look at this. Now remember, the way a vector field works, this is f and this is g. Okay, and this one's f and this one's g for that particular problem. All right, so f sub y would be the derivative of f with respect to y, which is negative 1. Is that in fact equal to, so I'll put a question mark because I don't know, g sub x? G sub x is 1, and those are not equal to each other. So this is no, and therefore it's not conservative. Okay, now let's test the next one. So f sub y, is that in fact equal to g sub x? F sub y would be the derivative of this with respect to y. So the derivative of the first term is 0, so that's nothing. And then this, we would bring the 2 down. 2 times 2 is 4, 4xy. And then here, the derivative of this with respect to x, this term would be 0, this term would be 0, this would be 4xy. So they are in fact equal. So f is conservative. I should have written up here f, not conservative, f conservative. All right, now since f is conservative, we can then find the potential function phi. Now the gradient of phi is equal to, let me grab a pen here, finding phi. So remember, the gradient of phi is equal to our vector field. Now the gradient of phi, the gradient, if you remember, is the partial derivative of phi with respect to x, and the partial derivative of phi with respect to y is equal to my vector field, which was, let's see, 4x cubed plus 2xy squared, and then 2y plus 2x squared y plus 3. Okay, so we're going to set the x components equal to each other. So this component equal to this component. So I take the partial derivative of phi divided by the x, partial derivative with respect to x, is equal to 4x cubed plus 2xy squared. And then what we do is we multiply both sides by the differential in the denominator. So this comes out of here. So we multiply by dx to both sides, and we just put it over here. And then we integrate, right? So what we're going to have is, here, let me write it this way. So you're going to have the integral of both sides, like that, right? And it just becomes dx over here. Right? So you multiply both sides by the differential, and then you integrate. So when you integrate partial derivative with respect to phi, or d phi, if you will, so when you integrate d phi, you're just going to get phi. and that's equal to, and we're going to integrate this with respect to x. So this would be x to the fourth plus x squared, right, because we add 1 to the power and divide, y squared, plus some constant of y, because I have, I'm only integrating with respect to x, so there's some other piece to this. Okay, now I'm going to do it again for the other side. So let's look at these two pieces over here. So I take the partial of phi with respect to y, and that's equal to 2y plus 2x squared y plus 3. I multiply both sides by the dy differential. It doesn't really matter if it's delta or d. And then I'm going to integrate both sides of that. So the integration of d phi is phi equals, and then I'm integrating this with respect to y. So add 1 to the power, so y squared plus x squared y squared plus 3y plus some constant of x. Okay, so what you do is you put together the pieces that you have. So you'll notice that both of them have this x squared y squared, right? So your phi is for sure going to have an x squared y squared plus, and then you're picking up the other components. So over here, there was an x to the fourth by itself. That's what the c of x is. That c of x is that x to the fourth. So you're just going to throw that on there, x to the fourth. And then you're also going to throw on your function of y, but your functions of y are right here. Those two pieces are your c of y. So you're going to add on y squared plus a 3y. All of those components together make your potential function phi. So in other words, you integrate with respect to x for the first component, and then you integrate with respect to y on the second component. Anything they have in common, you write one time. Anything only one of them has, you write it. And anything the other one has, you write it. And there you go. Now let's try to do it in 3 dimensions. Okay, so we need, let's just write it out. We need f y to be equal to g sub x. We need f z to be equal to h sub x. And we need gz to be equal to h sub y. I'm going to guess this one's a no because I didn't leave a lot of space. So fy would be the derivative with respect to y. So fy is 2. 2 is in fact equal to, oh, and don't forget, this is f, this is g, this is h right here. So the derivative of g with respect to x is also 2. So this one's okay. Now fz is negative 1. H sub x is 2. That's a no, and we're done, right? F is not conservative. All right, now what about D? Okay, so again, I'm going to write them out. I need f sub y equal to g sub x. I need f sub z equal to h sub x. And I need g sub z equal to h sub y. Okay, f sub y, let me label these again. This is f, this is g, this is h over here. Okay, f sub y would be z. G sub x would also be z, so that one's okay. F sub z would be y. H sub x would be y, so that one's okay. G sub z would be x. H sub y would be x. All right, so F is conservative. Therefore, we can find phi. All right, so let's write it out. So the gradient of phi is equal to our vector field. So the gradient of phi, which is the partial derivative of phi with respect to x, the partial derivative of phi with respect to y, the partial derivative of phi with respect to z, is equal to our vector field, yz minus x, xz xy plus 2. So we're going to integrate each of the components. So it ends up becoming, first one would be the partial phi with respect to x equals yz minus x. And then the partial phi with respect to y equals xz. And then the partial phi with respect to z equals xy plus 2. Okay, so then the next step would be to get the dx over there. So partial phi equals yz minus x dz, or it's me, dx. This would be the partial phi, oops, I'm putting my phi first. Partial phi equals xz dy. Okay, let me separate these with the lines you can see. And then the partial phi with respect to z, so xy plus 2 in parentheses dz. And again, it doesn't really matter about delta versus d. It's kind of a notational trick, so it doesn't make any difference. All right, so then we're going to integrate both sides of every single one of these. Okay, so when we integrate, we get phi, right? So all of these are going to be phi, pieces of phi. So I'm going to integrate this with respect to x. So that would be xyz minus 1/2 x squared plus some constant function, some function of the two variables I didn't use, which were y and z. This one will just be xyz plus some constant function multiple of, it's not really a constant, it's some function of x and z. It's just that x and z were considered constants as far as y was concerned. And then this one will be xyz, there we go, plus 2z plus some function of, we were doing with respect to z here, so x and y. Okay, so now putting these together, I guess I didn't need these lines to go as long as they did. So putting these together, we can come up with phi. Phi will be a component of all of them. So anything they have in common, like x, y, z, that's going to be there. And then anything they don't have in common but is in one of them. So I guess I shouldn't have written a plus sign because the next one will be a minus 1/2 x squared. Right, that's the only thing this one had to add. This one doesn't have anything, plus 2z. And if you're interested, the c of xy is probably this one. Right, that's the c of xy. And the c of yz and the c of xz, you could say one of them doesn't exist, and then the other one is 2z, like that. So there you go. And one of them 0 for our purposes. The important part is that anything they have in common, you write it one time. And then anything they don't have in common that's only in one of them, you write those as well. And that will give you your potential function phi.